Hey friends, it's me. It's Dan Marshall from the Met Opera's Education Department. I am so delighted to be here with you today for another exciting pop-up professional development, or as we like to call it, pop-up PD. Thanks for being here. Thanks for joining us for this wonderful lesson by one of my favorite teachers in our HD Lyman Schools National Network of Educators. As an offerance of accessibility, my pronouns are he, him. I am a white man with increasingly salt and pepper hair. I have a mustache and a little scruff on my face. I'm wearing a black Voices Rise Met Opera t-shirt. And in the background of my screen, there is a photograph of an elephant and some old New Yorker covers and an IKEA mirror. I hope you enjoy that. So I'm going to dive right in and bring to the screen Martin Richter, who is our friend and colleague from North Hills School District in Philadelphia, or I'm sorry, Philadelphia. My gosh, Martin, forgive me, Pittsburgh, outside of Pittsburgh. I'm so happy to have him here. And let me just get him in here. Hey, Martin. Oh my gosh, that Philadelphia gaffe is going to haunt me.
Oh my.
Oh, brother. Oh my. We do have friends in Philadelphia who are members of HD Live in Schools, but they're not here today. Well, maybe they're watching. Hi, everyone. Everyone, before we get started with Martin, I'll just describe that Martin is a handsome white gentleman in a white button-down shirt. He opted to wear a royal blue tie today, and the background of his Zoom screen, or Zoom, we're not in Zoom, we're in StreamYard, is a mini blinds, and it looks like a lamp and a bookshelf. So Martin, I know you have a wonderful lesson today about one of my favorite 20th century operas, Dr. Atomic, and I'm just gonna let you roll with it because I love what you do. So I'll see you on the flip side and have a great time.
Oh, well, thank you, Dan. And thank you, Kamala, and Marcia, and the entire Med Education staff for inviting me to present today. I'm delighted to be with all of you. Well, teaching opera presents a great opportunity to help students make connections beyond music to topics that span the entire curriculum. And John Adams' opera, Dr. Atomic, is especially helpful in this regard. You can partner with social studies and literature teachers because, in addition to tracing the factual history of the Manhattan Project and World War II, Peter Sellers' rich libretto makes reference to other eras and other cultures in the forms of poetry and mythology. There is also, of course, the great fascination with Big Thing Go Boom, or as they call it in academia, the science of particle physics, spoil sports. Well, the mathematical aspect is equally intriguing. And yes, we are going to talk about math today. And I hear you out there hyperventilating. Do not worry. The actual math part of what we'll be dealing with is really easy. You can even use a calculator if you want to do all the actual ciphering. And if it makes you more comfortable, find the math teacher down the hall to be a part of your opera team for this special exploration. In fact, get the whole gang together because today we're going to dive into the wacky world of Fermi estimation. So, have you calmed down about the math part yet? Good. Well, first, let's turn our attention to something a little less complicated: infinity. Okay, so this is the cosmic part of today's presentation, but I hope you'll still find it practical in your teaching. Infinity is a beguiling notion to us mortals. That's why it makes an appearance in so many literary works as well as several operas. The Flying Dutchman, Das Rheingold, Faust, and Mephistopheles, to drop a few names. Dr. Atomic is also about the infinite, the tiny atom, and its counterpart, the most colossal explosion ever created. Peter Sellers' libretto considers this contrast directly as we approach the actual detonation of the A bomb. More significantly, Sellers prompts us to ponder infinity through the lens of a variety of cultures, including references to the Mahabharata of ancient India and Pueblo Tewa poetry. This is, in turn, perhaps another species of infinity, juxtaposing the timelessly ancient with the terrifyingly futuristic invention. So, this is part of our fascination with infinity. It's a paradox. I mean, how can infinity be both the largest, like the bomb, and the smallest, like the atom, the most ancient and the most ultramodern all at the same time? It seems to be the opposite of itself. Well, it's not some Turindo riddle. I'll give you the short answer to the paradox. It's that infinity is not a number. Numbers represent fixed amounts, and who can put their finger on infinity? Much like Richard Wagner, infinity just doesn't stop. It traces a path. Infinity is not a number, but instead it is a concept that describes a lack of limitations. The in part means not, and the finity, finite, finite means finish or limit, unlimited. Numbers are, by their definition, limited by their exactness. When we seek to understand the extremes of our universe, as did Dr. Atomic himself, precise numbers cease to be really meaningful. While they can help us to approach some understanding, fixed quantities are ultimately defeated by the concept that has no limits. So, what serves us better? Well, rather than nailing down an exact number, making an estimate helps to inform us and to create a general boundary that allows us to make sense of things that are excessive enough to defy comprehension. An estimate is exactly what the scientists of the Manhattan Project did when it came to understanding their new and frightening invention. Incidentally, the infinity paradox is a good question to pull out when you need to keep the really smart kids occupied while you work with everybody else. Let them stew on it for a while. Well, now that we have infinity safely under control, let's look in on the opera as Dr. Edward Teller considers the strength of the new weapon.
Fermi is taking wagers as to whether the bomb will ignite the atmosphere. And if so, whether it will destroy just New Mexico or the entire world. I failed to appreciate your black humor, Dr. Teller. This is exactly the kind of loose talk that might paralyze enlisted men with fright. Edward's a great one for oddball problems, General. I asked for, and I obtained, a most important assignment, one that many consider superfluous. There had been some suggestions that we might have miscalculated, that the explosion could be much larger than we had anticipated. Might we not be setting off a huge chain reaction that will encircle the globe in a sea of fire? It's my job to make a last check and review. In July, 3 years ago, of the initial calculations, and my figures indicated that the bomb would indeed create enough heat to ignite the Earth's atmosphere.
Nobody knew how strong the blast would be. After a while, all the scientists get in on the action, trying to predict the magnitude of the blast.
We have an informal betting pool going. Everybody puts in $1. Whoever guesses the explosive yield is a rich man.
I guess 300 tons of TNT.
A very low estimate. Not much more than 30 10-ton blockbuster bombs. In other words, what you're predicting is we'll get nothing more than a fizzle.
I confess my utter amazement that these scientists are glooming over their coffee cups about their uncertainties on the coming test.
The bomb has a blackboard potential of nearly 20,000 tons. That's 20 kilotons of TNT.
No one thinks for a minute we'll achieve a yield like that.
Beta and Ulam guess small, 5 to 7 kilotons. The scientists refuse to believe what their own calculations tell them.
I confess that I am not optimistic myself. Maybe a 40-60 chance of success.
I alone scoff at my colleagues' pessimism. I pick 45 kilotons.
So that Dr. Teller is some sport, huh? Risking a whole $1 and to bet on mass destruction. Why couldn't they just do a March Madness pool like everybody else? Well, the real problem was actually that they might never have been able to figure out just who would win the big bet. You see, the blast would probably be strong enough, to wreck any instruments that could even measure it. And that's where our friend Enrico Fermi comes in. So, who was Enrico Fermi? He was an Italian physicist who got to America before the war started. He won the Nobel Prize in 1938 and had taught at both Columbia University and at the University of Chicago, where our nation's premier physics institute, Fermilab, still lives. That's it on the left. It looks like there should probably be a monorail leading to it or something. His contributions to science were so great that they even named chemical element number 100 after him, fermium. And since Father's Day is coming up, I'll tell you that naming an element for Dad is a way better tribute than the International Star Registry. Okay, so the opera only name checks Fermi twice, but he was an incredibly important member of the Manhattan Project. Fermi was especially known for his ability to estimate gigantic or long-range entities, starting with little or no actual data. What he would do is he would gather small, measurable calculations for a short term, and then multiply them to project them out for an estimate for a longer period. Now, the story goes that during the Trinity bomb test that ends the opera, Fermi dropped a few little scraps of paper at various times during the blast. Just by measuring how far the shock wave carried the scraps, he was able to estimate the strength of the atomic bomb. Now, when I first heard this, I thought, oh yeah, this is just one of these stories. But after doing a little bit more digging, um, I found the actual log entry about his estimation, and here it is. About 40 seconds after the explosion, the air blast reached me. I tried to estimate its strength by dropping from about 6 feet small pieces of paper before, during, and after the passage of the blast wave. Since, at the time, there was no wind, I could observe very distinctly and actually measure the displacement of the pieces of paper that were in the process of falling while the blast was passing. The shift was about 2.5 meters, which at the time I estimated to correspond to the blast that would be produced by 10,000 tons of TNT. How amazing that Fermi could estimate something so massive as the strength of an atomic blast just by using a few scraps of paper. So now, here is where your students can use Fermi's method to solve some pretty wild problems, some large enough to approach the infinite. Fermi's strategy, in a nutshell, was to start with small, knowable things and then extrapolate these, combine them, project them out to create larger entities. Now, to find these small things, break a gigantic question into its comprehensible components. You have to think, what small pieces of information would I need to know in order to solve the big problem? So, enormous problems are really just huge steaming piles of little knowable things. To show you what I mean, let's do a fairly simple problem that I use with my fourth graders. Using Fermi's method, estimate the number of Halloween candies you will get in your lifetime. So what do you need to decide? You need to figure out, oh, how many years will I trick or treat? How many houses will I hit each year? And finally, how many pieces of candy will I expect to get at each house? So, how many years will I trick or treat? We decided 9. I mean, you have to stop at some point. There is nothing sadder than seeing somebody my age showing up at your doorstep with an empty pillowcase and a Spider-Man costume. Then, how many houses will I hit each year? We figured 40. And how many pieces of candy at each house? Well, we couldn't agree on 2 or 3, so we split the difference to 2.5. The solution is therefore 9 years times 40 houses times 2.5 pieces of candy at every house comes to 900 candies. So there's a gold mine for some dentist. Now, why do we multiply to combine these numbers? Well, multi means many, and ply means layer, like a 2-ply tire. So think about a good layer cake. Each layer is the same size. That means that multiplication will apply to these types of for each situations where the same action is repeated over and over. Now, if you want to keep the kids humble, you might just want to swap out this question for how many pages of homework will you have in your lifetime? Ooh, scary. Well, here's an example that's a little bit more involved. How many heartbeats did Mozart have in his lifetime? Ooh, and cold as ice. Maybe he didn't have any. We'll have to ask Costanza. Well, to answer this, first we need to determine how many times a heart beats every minute. And here's where a little discussion starts, because students will likely know that sometimes your heart beats fast, like when you're running, and sometimes it beats more slowly, like when you sleep. Now, when everybody looked it up on Google or the reference books, We all found that the average heartbeat is about 70 beats per minute. Then we need to figure out how many minutes in a year.
500.
Okay, we're not going to do that. Uh, and in fact, my number is a little bigger than the one that Jonathan Larson got because Jonathan Larson was writing a musical and we are searching for the truth. And the truth is, of course, always a little bit bigger than you expect it to be. So what we found were 60 minutes in every hour, and then 24 hours in every day. And then this is where we differ from Rent. He figured on 365 days in a year, but we are adding the 0.25, the 1/4 of a day, because you take those 4 quarters, and that's why we have the leap day every 4 years. Okay, so now students need to find out how long Mozart lived. And upon looking that up, the answer is about 35 years, 10 months. And the 0.83 is 10 out of 12, 10 months out of 12. For those students who insist on precision, yeah, they're free to count the days. If they get too obsessive, just remind them that we are estimating, not seeking an exact answer. So now we can complete the estimation. We have 70 beats per minute times 60 minutes in an hour times 24 hours in a day times 365 1/4 days in a year times about 35.83 years comes to about 1,319,160,276 heartbeats. And if you are inclined to write the sequel to Rent, please understand that this could be the singularly worst lyric you could ever pick. So that is our estimate for how many heartbeats in Mozart's lifetime. Now, you'll notice that I use this really strange mathematical symbol that looks like two Pringles potato chips that are stacked on top of each other, rather than the equal sign. That is an approximation or an estimation sign because we are estimating, not calculating. I always figured that that kind of looked like an equal sign that was shrugging its shoulders, saying, I don't know, around this much, not exactly equal. Also, the round number helps us to make sense of the amount more so than some possibly exact number. All you really need to think about for your response is about 1.3 billion, because controlling the actual number would serve no practical purpose and is in fact more likely to get you lost in the weeds. So when students are collecting information, there are three places where they're likely to get it. There are things that they outright know, like how many minutes are in an hour. There are things that they can look up, such as the average number of heartbeats per minute. And then there are things where they could just take a really good guess about, like how many candies will they get at each house. I will have a Fermi worksheet for you, and this is appropriate for any age. You can use it for your students. There are spaces for them to show their problem-solving strategy, and also places for them to record where they source their information. I guess these questions can get pretty elaborate. My 4th grade did a group project one time. How many letters are in the school library? So for this one, the debate centered more on the methodology of finding the solution. What are the component parts of the answer? And what constitutes a representative sample of any of those? For instance, how many actual shelves worth of books would you need to hand count to get a good handle on the average number of books per shelf? So this was a major point of contention. At some point, you'd need to know how many words were on the average page. So will the number of words on a page be able to represent Dr. Seuss books in the easy section, as well as reference books like the dictionary? Well, after about 30 minutes of really good, serious planning, Each student was assigned a small piece of the task, and together we all barnstormed the school library. And yes, our librarian is still thanking us. When we regrouped, each student provided an individual piece of the puzzle, which we then combined to form some unbelievably large number. Now, certainly, students can explore Fermi math by formulating their own questions. Or why not use one of my examples? And these will also be available for you. I have a whole list. Here are a few samples. How many feet of pasta would be needed if all the students in your school had spaghetti for lunch? And I suppose you could do this in a gluten-free version as well. So think of what you would need to know for this. You would need to know the population of your school. And then maybe if you wanted to break down and spend 99 cents, you could get a pound of generic pasta and have the kids measure out, do some kind of lab work to figure out how many feet of pasta constitute one portion. Another type you could do would be how many ping pong balls would it take to fill the Washington Monument? And this is a volume problem that you can look up, or else if you wanted to do the volume of ping pong balls, you could do that with displacement in water. Talk to your science teacher about that uh, and figure that out. To do it by subtraction instead of addition, you could say, how many dump truck loads would it take to cart away Mount Everest? All right, so by now, you're probably wondering why you should even bother teaching a bunch of strange-o problems when, frankly, you have a music class to run. So let's get into the practicality of Fermi estimation. I'll explain for you why Fermi estimation appeals to young people. Then, how Fermi estimation can relate to the world of opera. And finally, why Fermi estimation is such a vital and practical skill for young people to learn. Developmentally, children have a natural fascination with extremes. Want to keep a 10-year-old quiet on a long car trip? Give him or her a copy of the Guinness Book of World Records. So why does this work? Because children have an innate desire to learn, to master, and ultimately to dream of exceeding the limits of their big world. This expresses itself in their fascination with video games. Video games represent an environment that they seek to control. Opera is also an art form of the extreme, which makes it a wonderful candidate for Fermi explorations. I suppose you could design a scavenger hunt to find the loudest, the longest, the highest, the lowest, the most people, the fewest people, some form of Guinness Book of Opera records. Well, the Fermi method also engenders a spirit of confidence in young people. It tells them that there is no problem too big to solve, and it nourishes that need to master and to one day control their world. They develop faith in their own power and ability. Additionally, kids love the sheer looniness of some of these problems. Turning our attention to the musical world, yes, you can utilize the Fermi method in musical analysis directly by asking students to estimate the number of notes in a Mozart opera or the average amount of words in a Rossini patter song versus a typical Gilbert and Sullivan. But there are far more important applications. Enrico Fermi himself connects narrowly with the subject of just this one opera, Dr. Atomic, but his method is incredibly useful in the entire world of opera, especially on the logistical and production end. Fermi estimation offers a window into the making of an opera production. What is required for the colossal art form to take the stage and to recognize the fiscal as well as the physical constraints involved. Here are some examples of Fermi questions that you might want to use with regard to opera. Can you estimate the number of people to populate a Zeffirelli crowd scene given the staging area. I mean, you really do not want to be staging Act Two of La Boheme as you see in this picture, and suddenly realize that you have a bunch of bare spots in the crowd, or even worse, have to send a bunch of supers home grumbling. Those supers are a vengeful lot. You need to figure all that out in advance before the meter starts running at your rehearsal. Or how many poppies would you need for the dream sequence in Prince Igor? And what will it cost to stage this scene? Maybe how many light bulbs to do the Vegas Rigoletto? How many hours of practice would it take you to learn the role of Mimi? Or how many beads do you need to make the Akhenaten costume? And given 30 days notice, at what rate of speed would you need to sew? Now notice that this question, as well as the Mimi question, deal with time as well as physical or economic resources. I mean, it starts your imagination going. You might well wonder how many hairs Anthony Roth Costanzo had to shave in order. Well, maybe that one's not such a good idea. But these others are all very practical things to consider, and they help young people appreciate just what goes into getting an opera up onto the stage. But even beyond the world of opera, Fermi estimation is useful to determine the logistics of situations and for data management. What constitutes a good random sample? How do we source info? Do we look it up? Do we do the actual field work? Do we conduct a survey? Do we rely on our experiential knowledge? There is a direct application to statistics of social sciences like public opinion polling, the STEAM subjects, especially engineering and production. Fermi questions encourage creative thinking involving different solution strategies, so they promote a range of problem-solving skills requiring students to be both logical and inventive. Fermi questions are open-ended problems with no exact answer and no definite solution. They're interesting, though. They motivate young people and they challenge and reward them. They create a culture, a mindset, a community of questioning and curiosity. This was very important for me, that you get a room full of active thinkers, and isn't that what you really want? Fermi help young people develop much needed estimation skills, which offer a sense of whether an answer is reasonable or not. Anyone involved in big picture planning, whether it's about the resources needed for a space flight to Mars, a random sampling for an election poll, or what it takes to actually mount a production of Dr. Atomic, regularly uses some form of Fermi estimation as a way of getting a ballpark idea of the viability of long-range plans and projects. Fine arts, literature, and history are easy connections with the world of opera. Fermi estimation offers a way in through math and an opportunity to include educators from other disciplines as you build your opera team. Fermi estimation teaches young people not to be intimidated by the most gargantuan nor the most microscopic things, the distant past nor the remote future. It allows them, like Dr. Atomic himself, to contemplate the immeasurably extreme with a mixture of wonder and awareness. It gives them the courage to try to grasp the infinite, even as it escapes. Most important, Fermi estimation sends young people the message that there is nothing beyond our ability to comprehend, whether it's the strength of an atomic blast or the majesty of grand opera. Fermi estimation is a powerful tool, and I hope you will choose to include it when teaching your young people. Thank you.
I was muted. I'm really knocking it out of the ballpark today. Martin, that was a wonderful lesson. Thank you so much. I'm using the Fermi estimation to figure out how many years I would have to go back to university to learn how to be the kind of pedagogue that you are. I can break it down, but I don't think I want to think about it. That was so wonderful, and it's so fun to sit inside this mind of yours that thinks of these links to opera that I never would have even considered, especially when we have an opera that is so STEAM oriented, like Dr. Atomic. So thank you for serving this community with this lesson today. I know teachers all over the country and all over the world even are going to get a lot out of this. So
thank you for the opportunity.
Oh, absolutely, absolutely. You are a treasure to the community of HD Live in School, sir. And I can't wait to see you in person, and I hope very soon.
So,
have a great day, Martin. Take care.
You too. Thank you.
Bye-bye. Friends, thank you so much for joining us today for another Pop-Up PD with Met Opera Education. We're just so proud to be able to present these master educators in their natural habitat, teaching teachers about opera and different points of entry for students all over the world. I'm so proud to be a partner with North Hills School District outside of Pittsburgh. Got it right this time. And so very proud to be part of this network of educators that includes people like the wonderful Martin Richter. Have a great day. Keep watching opera. And if you have any questions that you need answered, you can always email me at hdschools@medopera.org. All right, everyone. I will see you next time. Thank you. And thanks for joining us. Bye.